recording. All right, so today we're going to take a look at some machine learning. We're going to understand what this concept is, and we're going to look at two foundational models that inform a lot of things, from the way that Netflix picks a movie for you or Spotify decides that you should listen to this music, all the way to the very first start of what we call a neural network, right? Which is a huge thing in artificial intelligence. We talk about neural networks, the brains. We're going to review a little bit of stuff that we talked about at the beginning of the semester, but we're going to throw a bunch of new stuff on there as well. So I think this should be an exciting lecture. It might seem a bit abstract, and we're going to cover some concepts that are a little mathematical, but in a way that's very similar for this class. That I'm never going to ask you to kind of do the calculation. You need to understand from a theoretical perspective what's going on. Okay? Sound good? So specifically, we're going to talk about the perceptron and k nearest neighbors. And along the way, I'm going to give you some kind of best principle ways that we think about implementing any kind of algorithm. You did a little bit of reading about k nearest neighbors. Fist to 5. 5 means that I read the entire thing, I understood it, I took notes. Fist means I did not look at it. Where are we at? 4, 4, 4, 3, 3. Just before we jump in, what did we think about that reading? I know that a lot of us had found the Zaleski computer vision chapter difficult, and I tried to pick one that had very little math in it. So what did we think about the reading? It was 10 pages. Useful, not useful? Very useful? Who said very useful? Very useful, okay. If I had given you like a 20-minute YouTube video to watch instead, do you think you would have found that more useful or less useful? Less useful, okay.
I thought it was nice that this had just like a term and then it defined it.
Yeah. Defined it? Okay, yeah.
I mean, like, I think it always depends on like the topic of like what I'm looking at. But, like,
Okay.
a YouTube video can be helpful if I can understand it.
Yeah, I'm linking other YouTube videos into the like section that isn't required, but more stuff. I'm somebody who actually, honestly learns better from videos, but it's good to hear that the readings are really helpful for people as well. I usually start with videos and then go to readings, if that makes sense. All right, so starting point. What are we talking about when we're talking about machine learning? It's such a vague concept. It's like artificial intelligence. People talk about it, and sometimes it seems like it's just a way to sell things, right? And you don't actually know what's happening. So in traditional approaches to maybe like computer science or economics, we have to design a system, right? And we design it from the ground up. So say let's go back to an example in computer vision. Say we're taking an image and we want to convert it from a JPEG to a PNG, right? Very simple, just changing the file type. Well, we have to design a system that does it, that goes in at the pixel level, reads all those pixels, and then changes like the compression algorithm to get to a PNG. That would be like a traditional approach. In machine learning, we take the radical step of allowing the machine to kind of design the system itself. And we're going to talk a lot about how you can do that, how you can trust it, and then how much control you have in that interaction. So this is a very simple example. We always start with a hypothesis. In this case, we're trying to think through, if you spend more time studying for my midterm, will that correlate to a higher grade? And specifically, we don't want to just say yes or no. We want to know specifically, because this is, time is a zero-sum game. You want to know exactly, I could show you that 3 hours is the optimal amount of time that you should spend studying, right? And so we want to go through and we want to state a general hypothesis that the more we study, the higher score we're going to get. We want to collect a bunch of data points from past students who have done well or not so well. This is a pretty bad score, I'd say. That's a pretty good one. And then we want to try to let the machine learn a model that can predict a little bit, right? We're trying to solve for these two variables. If you go back all the way back to grade school, when you first learned about like slope, you might have done something where you had a ruler and you had to trace a line. This might be, did anybody have to do something like that? Yeah, you try to find the line of best fit. Well, here in machine learning, we're going to let the algorithm try to find that line. And not surprisingly, we'll often have to try many different lines to find the right one. So ideally, what we want to find is a line that goes through all these data points, right? And then the question is, well, how off or what is the error of that line? And to calculate the error, we just take the distance from each one of the data points to our kind of best fit line. Does that make sense? Technically, we do something called squaring the error because it gets rid of the negative values. We don't really need to cover why we use a mean square error, but this is a pretty simple idea, right? If we need to know what is the error between our model, which is this line, and this data point, we'll see that there is more variance there than there certainly is here, where it's right on the line. We feeling good so far? This is not very complicated, right? So, and we square the errors basically so the negatives don't cancel out the positives. That's why they're squared, because when you square a negative number, it becomes a positive. Okay, any questions thus far? Feeling good? So one thing that we can begin to do as we do this, we fit a bunch of these different lines, right? And every time we fit a random line, we measure the distance, is we'll start to get basically a function of the error, right? Every time you do it, you'll be able to calculate what the error term is. And as you do it a lot, your error will start to have this kind of parabolic shape or this U shape. Does that make sense? Okay, so we've went from trying a bunch of these different models to picking one that works really well, and we didn't just randomly pick it. We used an error term, right? We summed all the squared error terms together, and then every time we did that, we picked a new line that we thought would minimize the error. And as we did that, we started to get this nice function where the minimized error, our best fit line, is at the bottom of the bowl, so to speak. Does this make sense? How many people have seen this before? Maybe in an economics class? Kind of, sort of? Not so much? In physics at all?
Not directly.
Computer science at all? Kind of, sort of? Good. We're all learning something new today, right? So far, not too complicated? So could somebody explain to me why this looks like a U? Yeah, because basically we're going to start with a line over here. There are going to be a ton of errors, and then we're going to overcorrect probably above it. We'll get a ton of errors, and we do this kind of oscillating thing until we get right to the best fit. Does that make sense? So the bottom of the bowl is a place where our error function, as calculated by the distance between our slope line and the actual data points, is minimum. So how do we try to throw all these different lines to fit our data? Well, we could just go through each time and make a little change, but instead that takes a lot of time. In this little GIF, you can see we could do 40 of them, or we could decide to calculate the slope at this curve. In other words, take a derivative, which we've covered in class already, and then we could have basically a learning rate. And the learning rate is going to be how far along you hop each time rather than just randomly moving, right? Because the idea that random movement or movement at a set interval is going to take a lot of time. Say you just say, I'm going to take this and I'm going to divide it into 100 segments and go through each time. Well, that's a lot. If you have a learning rate, you'll see each one of these dots starts to get smaller and smaller, and we can find it in about 6.7 iterations rather than 40 or 50. So gradient descent is that way of coming down the slope to find the bottom of the bowl. And once we have that, we have an equation, we have a slope through our data that probably is going to be our best fit. Now that learning rate, how many times we jump down, we get to control that generally in machine learning. So we get to say, this is how fast, Mr. Algorithm, I need you to solve for this problem. This is how far you can jump along that bowl. And we try to find a learning rate that basically is going to be getting us down to the bottom of the bowl quickly and also accurately. So we're not like shooting around and you see this one overshoots just a bit. So our learning rate is typically expressed in terms of this alpha term. Does that make sense?
So wait, can you go
Yes.
back for 1 second? So that's just, the learning rate is based off of, like, us just playing around and finding the right, like, I guess just like the best
Hyperparameters.
error, like
Yeah. These like, we've talked a lot about knobs that you can turn.
Yeah.
And these are some knobs that you get to turn. Because the idea behind machine algorithm is you're going to let the machine or the algorithm try to solve it. And these are the steps of control that you have. And so we get to express our learning rate in terms of how far it's going to leap each time as it calculates those mean sum errors or mean square errors. And then we want to make sure that when we're doing this, that we don't fall into the trap of overfitting or underfitting our model. And this is pretty important because our data set that we derive in the case of students studying hours, time put in versus exam, this is not all students at Hampden-Sydney, right? This is just a small subset of the data that we're going to try to model our algorithm on. But we need to make sure that our algorithm actually works in real life, right? Which means that we don't want to have a algorithm that neatly hits every point, because that overfits our that'll overfit. That'll basically will not be transferable to real life, right? So you can teach a algorithm to have a 0% error rate, and you can find a learning rate, and if you're not careful in terms of what you select as your data set, you can get it to work perfectly on your data set. It memorizes every association it needs to, but then it doesn't perform well in real life. It looks perfect, but it doesn't transfer over to other data sets. So you're working on a fish detection algorithm, and you make one that works perfect for the fish that I give you. But then when we go out in the real world, it can't detect fish, right? You have a player tracking algorithm that you develop based on the basketball team at Hampden City, and it does perfectly in Kirby. But maybe you didn't think about the fact that the incident light, because you're going to use a color-based system, is different when you go to Randolph-Macon. And all of a sudden, your data set does not work at all. You make a face detection algorithm to unlock your phone because you're working for Nokia in like the mid-90s and early 2000s. And it works great for Norwegians and Swedish people. But folks like in America or North Africa can't unlock the phone with their face because you train the data set on a bunch of white people faces. Does that make sense? These are all examples of overfitting. Questions, comments? Still feeling good? All right. And obviously for the econ business people, there are reasons why you don't want to overfit models. Yeah, man, I train on a bunch of, I'm going to try to predict NVIDIA stock. I trained a bunch on it. I have an overfitting model, and now it can't deal with like the variety and types of differences that we get in real life, and I just lost a bunch of money. So how do we stop from overfitting? Well, one thing is we don't have it trained on all of our data, right? We might hold some of that data out, train it on like 80% of the data, get an algorithm in which we minimize the error rate and we're pretty happy, and then have it look at some data that it never looked at before. Does that make sense? Which is why when thinking about data sets, we typically have this kind of rule that between 70 and 80% of the data we're going to reserve for just training our models, and then we'll split up basically testing data sets where we show it. And the validation data set is where we get to decide like the hyperparameters, like what should our learning rate be, right? So we go through, we hit our training data set, we train our model, then we train our hyperparameters, like our learning rate on validation, and then we test it on a bunch of data it's never seen before. Yes?
So if I was doing like a snowfall detection thing,
Mm-hmm.
so the camera I use is the one that like for my data set is the same one I'm going to be looking at to check whether it's snowing or not.
Yeah.
So does that mean I want to get a different data set?
This is a really good question. So it kind of depends on the algorithm that you use. In some applications, the camera that you collect the data with, we have to randomize the cameras, or even take the images and then do things like blur them a little bit, or change the hue, saturation, contrast, like augment the image data in a way so that we don't just get a camera or a model that's really good at identifying that it's actually this type of camera. I'll give you an example. One of the first projects I remember working on was I was trying to develop a model, a neural network that could recognize small boats, like small aluminum skiffs, because they go missing a lot in Alaska. So it was supposed to be running on a drone, and it could find it. And what I kind of came up with this idea after I had been in Quinhagak, and we've been doing a bunch of drone mapping for archaeology. And one of the things that one of the pilots he really liked making cinematic shots of us driving the boat up and parking. And I was like, perfect, I've got a huge data set. I have like probably 6 or 7 gigabytes of video data of just boats from all different angles. This is perfect. So I took those videos, I split them into images. So I had like 40, 50,000 images. And I went through and I labeled each one with a bounding box. It took I did it over spring break. And my wife was like, are we gonna do anything interesting? And I was like, no, I just gotta label more boats, right? And what I ended up doing was training a neural network that was really good at predicting the middle of an image. It could tell you where the middle of an image was, no problem. It was not able to predict boats at all, even though I had trained it on a bunch of boat data. Why do you think it overfit to that? He always centered it up because he was, flying little drone movies, and we typically put the thing in the center of the image that we want to see, right? And so the next iteration of that, I basically masked the boats. I put a mask around them, and then took that out of the image, and then took a bunch of blank backgrounds of the ocean and started putting boats in random places. It's called synthetic data generation, specifically cut, paste, learn. And now the neural network can't just say, yeah, I go to the center of the image and I always find the thing I want. So that question of should I vary the low-level parameters of my image, the focal length, the aperture, the hue, the contrast, the saturation, the contrast, typically, yeah, because we don't want our algorithm to just learn those and be like, I'm supposed to be tracking a ball, but the ball is always blue. So in fact, what I have is an algorithm that detects blueness. Does that make sense? Or even because a lot of these actually read grayscale images, they don't even worry about the other tensors. I'm supposed to be tracking players, right? Ned wants to do some player tracking for this class. But what I end up doing is just realizing that there's a gradient contrast between the floor, the court floor, and the players. And so I just learned that contrast. But then when we go to a different stadium where maybe the wooden basketball floor is a different color, and now it doesn't work. Those would all be examples of overfitting. Does that make sense? Yeah, so I like to think about this I forgot to grab my deck of cards, but I use decks of cards to use this. So I have a bunch of decks of cards, and I have no idea if I just bought it new and they're all in order. I have no idea if somebody shuffled them before, but the very first thing, before I even worry about that, is I might want to, just like when you're playing poker, someone cuts the deck, I'm going to cut the deck, and I'm going to put this over here, and that's our test and validation, and then I'm going to give it to you, and I'm going to say, memorize all these cards. Or tell me if you see a pattern in all these cards. And you'd be like, yeah, I see the pattern. There's a brand new deck, so it goes, 2 to ace, and it goes spades, hearts, whatnot. Does that make sense? And then I'll okay, you think you got it? Look at these. Tell me if you can predict based on that, that what they are. Does that make sense? So one thing, going to our deck analogy, is we also have to make sure when we make that split that we don't accidentally have any biases in the data set. So I think the card analogy is a really good example. If I bought a brand new deck of cards, they're all going to be in suit order and numerical order. Well, if I just made that simple split, and I told someone, memorize these cards, they'd probably memorize that order. And that would not be good because when you go out into real life, most decks of cards you're going to see are not going to be like that. So what I might do instead is while I'm making my holdout data sets, we call these holdout data sets, I'll go ahead and I'll basically shuffle it, and then I'll count 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. Shuffle it. And that's with the K fold each time. Shuffle it. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. Shuffle it. And the number of shuffles you have, the number of cuts, is the K folds in your data set. Does that make sense? So let's say that we're doing face detection again, right, for unlocking a cell phone. We know that we're going to have a variety of skin types, and that's good because we want an algorithm that isn't overfitted to a certain skin tone. Well, we might want to make sure basically we mix that data set together. So if the way that we did it was we sent people out into different countries and took pictures of people's face, that we're not training on, let's say, America, Armenia, Britain, and Deutschland, right? Because say we did it alphabetically. But then in our testing data set, we have China, Ghana, other countries where we might have slightly different features. Does that make sense? K folds. So when we actually do our machine learning, our algorithm, we have our learning rate, and we train it on algorithm A and B. And then the validation step is actually we get to pick what of these parameters in terms of learning rate work best. So think about your validation data set as a holdout data set just like the test, but it's for really refining the model, making sure that we're not overfitting. And then we'll show it to the test data set. And that stuff should be brand new, and it should also be representative of what we're training on. Right now, Jabba and I are working on a project where we've taken a bunch of those drone orthomosaics. We image stitched them together using a program that uses SIF, SURF, and ORB, and we're labeling polygons of different vegetation there. And one of the things we're going to have to do is we're going to have to make sure that when we train the model, that we leave out some of those polygons of different vegetation so that we can see if it can predict it really well. So just a summary, we have a hypothesis. We try to measure the error of our algorithm. We try to reduce the error with gradient descent and learning rate. We use the validation data set to help do that. And then we split the data and we test on stuff that the algorithm has not seen. If we can do that well, we can kind of close the domain gap, so to speak, between real world and our data set. Make sense? Is this different than what you all have seen in math or econ business stuff before? Kind of, sort of? When you guys, how many of you are econ majors again? Raise your hand. When you calculate a loss function, how do you do it? Is that something you've done?
Not that I'm aware
Not that you're aware of, yeah.
Maybe.
Maybe. Well, now you know how to do it, right? And there's a lot of applicability. This is what quants do, basically. This is the whole science behind it. Yeah.
When we're running regressions, it's kind of similar. You'll do an ex post forecast, and then you kind of save some of the data after to see how well the model tracks. You have maybe the 60 years prior and save 10 years at the end to see how your model did. It's kind of similar.
Yeah, and I think we're starting to get there. With machine learning, the idea is that we do that thousands of times, and then we pick the best model. So I think right now you're learning how to do it where you control it, and you try to model the line that goes through. And in machine learning, we just basically say, do it iteratively. I don't care if you have to do it 1,000,000 times. Just keep doing it. And then every time you do that gradient descent, and we'll get to a place that as long as our data set is representative of the phenomena, we should be able to get to a place where we have a model that is more accurate. So there are basically two foundational types of models. Yes?
Is gradient descent the only way you can find
Calculate the loss function.
other methods?
Yeah, we're not going to cover a lot of things that don't use gradient descent. But we will look at two different ways of calculating even today, we're going to look at a couple different ways of basically deciding how the algorithm decides to make a grouping. And this is actually leading us right into this concept, that there are basically two different ways that we could do this. We have parametric and non-parametric models. The Perceptron has parameters, and k-nearest neighbors, which you read about today, does not. And I like to think about it this way, is like, let's take a metaphor of learning how to cook. In a parametric model, once we learn the recipe, we don't ever pull the cookbook out again, or the training data set. We say, I can learn that function, and once I know that, I don't need anything else, right? Just give me the new data points, and I'll plot it on that point. This would be something I think that's similar to maybe what you've done in economics. With algorithm like k-nearest neighbors, we keep the cookbook, and we look at the data set every time that we make our inference. So this is obviously one in which we make very little assumptions about the data set, and we kind of need the data set, which has some really beautiful properties, but also means that it can take a little bit longer because you're going through a lot of instances when you actually run the model. So the data is the model, versus once you have the data, you can get rid of it because you have the general pattern that you need to work through. And I picked two models today that kind of illustrate these things back to back. So yeah, in here, once we have it, we're good to go. We got that general direction, and we know the slope and the intercept, so we can, just keep that and have a new student and predict their score. It's pretty nice, pretty convenient, can be pretty fast. And non-parametric like k-nearest neighbors or nearest neighbors, we don't really have a slope, so to speak. We might be doing like just general grouping. So we have that, and we're calculating, this is our new data point, and we're just calculating distance from it. So you see why you need your data set for that. So yeah, this is more for you to review for the midterm, and you'll probably see this in some kind of study guide or things like that, but just getting you to think through this basic division. Covered a lot of ground so far, although I think it's a good gentle ease into some more complicated things now. Are there any questions that I can answer before we look at two specific models? All right, fist 5. 5 means I'm feeling pretty confident. All right. I'm going to check back in like 20. Where you at, Evan?
Like 3-ish.
3-ish. Anybody 3 or below, raise your hand. Okay, that's fine. Yeah.
So, I mean, like, I understand a lot of it conceptually, but like in terms of like actually
Doing it?
applying this to something, like what's the like basically input and then what's the output? Like,
We might look at a bunch of examples of that right now, because we can describe it in theory, but then we probably want to take a look at something like the Perceptron and be able to understand what is going on. And we probably want to look at the very specific inputs here so that we can begin to see. So we covered this, a version of this slide was like way back on the first lecture. We looked at it and I explained that, folks as early as like 1956 with Rosenblatt and had developed this kind of computational equation to a actual neuron in your brain, where the idea was that you took a bunch of inputs into a system, and those would be like basically columns in a spreadsheet, and every row is an instance of that, and we multiply them by some weight, and that's the thing that the model learns, right? The weight. How important is this column versus this column? Is this column twice as more important than that one? That's your weight term. Then we have a general bias term, which we'll get into. We basically put those in to a function, and if it hits a certain threshold that we've decided is important, then it goes forward. Just the way that a neuron takes a bunch of inputs, and then if it kind of sums to a certain place, it fires across the synaptic gap. That was the general idea. And this is like a neural network is a combination of these, where you flow through kind of a grid flow. There's some math involved. We don't really need to be really fluent in what these kind of things mean, but I will explain what they mean. So Y is our labeled data, right? Because in machine learning and supervised learning, we give it labels. We're going to look at a bunch of labels today. So this one would be like, did they survive or not? Those are our labels. We want a Perceptron algorithm that can take these inputs, look at train crashes, for example, and then be able to predict whether you'll survive the train crash or not. That's what our Y-turn is. And then we're going to sum up, that's what the sigma is, the inputs, our columns, by our weights, which the model learns, plus our bias. And if this equals the threshold we set, go. And we'll take a lot of time to break this down. Yeah.
Are you gonna come back to KNN?
Yeah, that's the last thing we're doing today. We're going to do Perceptron first and then KNN. So the first concept I want us to be familiar with is something we've already seen already. Some of my math colleagues might say this isn't technically isomorphism, but forgive me. I showed you two ways of looking at an image, right? Projected in a 3D coordinate space and a 2D coordinate space. The actual values did not change, right? Remember, z-axis was pixel intensity, and that's what we see in the 2D plane. It's almost like we have two different ways of looking at a concept, and being able to switch between those two different ways is how we get things done. So we can have a phenomenon we're trying to describe, and we can look at it in more than one way, but the actual data or the actual structure has not changed. It's known as isomorphism. Your hands are also isomorphic. DNA is isomorphic. It's this kind of ability that there is a structural relationship between two things, but we can visualize it in different ways, or we can solve it in different ways. And we have to be very comfortable with this concept, because a lot of machine learning is being able to think about things in terms of geometry, but also algebra. And we can actually solve it two different ways. And I want to start with a very simple example. Let's say, we don't need machine learning for this. Let's say a man walked due east 4 miles, and then he turned and he went due north 3 miles. Where is he, and how far did he walk as the crow flies? Does this make sense? And you could be like, I'm going to solve this geometrically. It's pretty simple. He made a triangle. And as the crow flies, that is the length in which he traveled, right? And I can draw it out, and I could count out the number of things, and I could come to a geometric solution here. And basically, we can think about these arrows as a form of magnitude, like a direction in which you go. And scalars in machine learning or in linear algebra are these things that are like 5 miles. They're just a constant value, 5 miles, 3 miles, 2 miles. But vectors are expressed in terms of their points in space. So he ends up at 4, 3. That's a vector coordinate. But he walked 5 miles. That's a scalar, right? Are we confident with the idea behind scalars and vectors? And the fact that you could solve this very simple problem geometrically. Is there a way we could solve for it algebraically? With algebra instead of geometry? Maybe with like a old Greek guy who squares things? Yeah, what does anyone remember the Pythagorean theorem?
A squared, is it times b squared?
Plus b squared.
Plus b squared equals
Z squared, right? And so you could calculate the hypotenuse of that triangle with algebra, right? And in fact, calculating magnitude of scalars is basically that. We have the Pythagorean theorem, but we don't want c squared, we just want c. So if we have a square, well, we could take a square root of these things. Some basic algebra, right? Feeling pretty confident, those who took like math for, calculus for econ. So we could solve for magnitude just to get our c term. He walked 5 miles by taking a square root of a squared and b squared. Both two ways to solve that problem, right? One is more algebraically, and one has more to do with geometry. Does that make sense? We could also add vectors up. So I could say that you walked 4 miles and then turned a little bit and walked a little bit longer, and we'd have to figure out where in the coordinate space you landed. And again, we could do the same thing. We could say, oh, you're at 6, 9, and we could calculate the magnitude or how far you went. Feeling good? Not too bad. So that's how we add. we could add vectors up geometrically. You could literally be like, I've got 2 vectors. I'm going to put them on a coordinate plane, and I'm going to trace them out, and then I'm going to count each one. Or you could probably do it algebraically. You could have a couple vectors, and you could add those 2 vectors together up this way. So we don't always need the geometric sense. Sometimes the geometric sense is really, really useful. Like when we talked about calculating mean square error, I think that's easier to see in a geometric sense. You could see them out on a plane and then the distance between the 2. I could have also shown it to you algebraically, and probably many of you have been like, I have no idea what the fuck I'm looking at. Does that make sense? Yeah.
Geometrically, you mean like taking the actual measurement?
Yeah, this is a geometric solution to that problem, and this is an algebraic one. This is something that you see a lot in probably your linear algebra class right now. Hopefully you're past this. But this is, we could solve the exact same thing geometrically with good old Pythagorean theorem. Does that make sense? We could also scale a vector, right? So we could say he walked a little bit, but then he walked 5 times the distance he already walked, right? And that would just be like taking this vector 4, 3, multiplying it by 5 to get our new coordinate place. And of course, we could do that algebraically like this, or we could plot it out geometrically. You see a theme here? And are we pretty comfortable that we know what a vector is? What's a vector?
A number that is like either with a value of size or direction.
Yes, yeah, absolutely. That is exactly. Vector has magnitude and direction, so it's going out in a place. And we typically think of vectors as these like combinations of numbers in a coordinate space, 20 and 15. But then we can do some algebra to the vectors too. And so if vectors have magnitude, orientation, magnitude and orientation, what's a scalar? Yeah, it's just a number. It doesn't have these kind of coordinates associated with it. It could be like the length of the vector. Cool. Feeling good? Probably you've dealt with vectors and stuff before in physics. So one other thing that we might need to know is when we're marching through the coordinate space, like the first example in the class was like hours studied and test score, we need to know what the units of this space are. We need to have some unit vectors. Those unit vectors could be, directional in terms of coordinate systems, north and east. They could be, in economics, hours and dollars, or in computer vision, they could be pixels. Does that make sense? So we have to have some kind of unit system that makes sense of our coordinate space. And once we understand that, now we can take those unit vectors and we can write a vector in a bunch of different ways that all mean the same thing. They all kind of have this isomorphism. We could write them how you probably remember seeing them in grade school. We could kind of write them in this column row, this format, which helps us a lot for doing like the kind of math that we saw algebraically, multiplying a scalar by a vector. Or we could talk about them in this unit vector form where it's like 4 hours plus $3, or 4 hours times $3, something like that. Yeah.
Can you like just clarify? Isomorphism is like you were saying it's like with your hands, like it's like 2 separate things.
Yeah.
They can be like looked at or like
Yeah.
viewed in a different way.
Yeah, I'm going to give a general definition of my isomorphism, then give a mathematical definition, and then show you that why I think it's important. So, like, if you're in a rhetoric class and I said that ask not what your country can do for you, but what you can do for your country, or it's not the size of the dog in the fight, but the size of the fight in the dog, you would say, like, there's something going on there. It almost is like we're mirroring this concept, and that would be a thing called chiasmus. So isomorphism is this kind of mirrored relationship, that there's a similarity there, but we might be transposing it in a different way that isn't exactly the same, right? And so mathematically, when we say something is isomorphic, we're saying that it has the same features. It might just be assembled in a way that looks a little different, right? Which is why I show you that example of 2 different ways of thinking about an image. What I am trying to get us to think of here is probably where a mathematician would say it's not technically isomorphic, but I'm saying that there are different ways that we can visualize problems. And for learning these machine learning algorithms, the big key that you need to have is that you can often visualize the problem geometrically on a coordinate plane, or you can represent it algebraically. And being able to switch between two is like very important. So it's not like there's one way to solve a problem. We can solve it multiple ways. So, oh man, it's like you answered a great question. You anticipated the next slide. I'm just showing you a bunch of different ways that we can algebraically represent a vector, or we can do it geometrically. And so think of our discussions all last week about pixels and computer vision. I was kind of switching between different types of representations without explaining this concept. And now we have to really understand it, because if we're going to actually build things that learn on images, we have to be comfortable with thinking about it in a geometric space, but also sometimes not getting super afraid when we see numbers like this. All right, so there's one other mathematical thing we have to learn, which is going to be foundational to the perceptron. And basically, it's how it decides whether to fire and basically move on and make a prediction or not. And that is something called the dot product. Geometrically, I think it's kind of easy to think about it this way. You have two vectors, and you want to see if you shine a light on vector B like this, and it casts a shadow down on vector A, where does it cast the shadow? And that's a geometric way to think of the dot product. It's like, as it casts that shadow, I like that because we talked about shadows and light, what we're really doing is we're saying how far apart are these two vectors. If vector B was up here and we cast a shadow, it's a longer line down to get down to where vector A is. Does that make sense? So the dot product is going to give us some kind of intuition for how far apart these things are. But we can also solve for a dot product algebraically, and that's what the perceptron is going to do. One important thing about dot products, and this shouldn't be super surprising, is if two things are orthogonal, or they come at 90 degrees, the dot product is 0. You can't really shine a light in any way where you get a projection there. And this is going to be very important, because the perceptron is basically, when it gets to a dot product of 0, it knows I'm good, basically. You can even think about the dot product here as like one way we could solve for it geometrically. And I'm getting into a little bit of trigonometry here, so if it bores you, I'm sorry. But we would maybe have a cosine angle here, and we could take the magnitude of both vectors, that like the square root of a squared plus b squared equals c, take the magnitude of both vectors, multiply them by that cosine, and then we would get the dot product. That's how we would solve it geometrically. But remember, the dot product is basically just telling us how close are these things together. If it's at 90, 0, and then if they're in the same line, it's 1, and then it'll scale up as they get further away from each other. So if we could take our data and we could represent it as vectors, we could start to calculate how far apart those vectors are from each other. Why might that be important? Yeah, so we could take our data and we could turn it into vectors for our machine learning algorithm to ingest, right? And if we had the dot product, we could see how far away vectors were from each other in terms of the dot product. Why might that be important? We could start grouping things. We could start saying, oh, all the stuff over in this coordinate space looks like it's related. And so if a new point that I've never seen before comes into the vector, into my coordinate system, and it's right around Evan, and we've labeled Evan as an Evan, it's probably another Evan, right? And if it comes all the way over here and it's starting to trend towards Jabal, and Dallin, and we've labeled those vectors as Jabals and Dallins. Well, we might need to calculate the distance between those and see who we're closer to. This is basically what a nearest neighbors algorithm is going to do. So I just said that we could also calculate a dot product without having the angle of theta geometrically. And this is very similar to how we're going to do it. We're going to have two vectors, A and B, and we're going to multiply A1 times B1 plus B2 times B1 times B2. That's how you calculate dot product algebraically. Yes?
So in training the model, are you just telling the model which vectors are related?
That's what the label is doing. It's saying that a bunch of these vectors, or a bunch of these edges, or corners, let's use corners. A bunch of these corners, we talked about corner detection. We could represent those corners, those individual corners, as vectors in coordinate space. And then we could say, all of those corners, that counts as dog. Those are a bunch of corners that are dog corners. And all of these corners, these are basketballs, right? That's what a basketball is. And all of these corners in these images, well, those are footballs. And then as we bring in new training data, and we decide that edges are how we're going to try to predict things, well, now our machine learning model can be like, okay, I have a good sense. I've been trained on what dogs are and what basketballs and what footballs are. So what is the relationship between those and this new data, right? And maybe it's like somewhere right around here and it gets a little complicated. Questions? That was like all the complicated math we had to do today. If it's 5, 5 means I get it. I know what a dot product is. I know what a scalar. I know what a vector is. Good. Those are things that I will need you to understand and be able to articulate in the midterm. If I ask you what a vector is, you'll say it has magnitude, it has length, and I'll be like, what are some different ways that we can represent a vector? And you'll be like, well, we could do it as like 4, 3 in coordinate space. We could do it as an arrow. We can do it both geometrically and algebraically. So let's get back to the Perceptron now. Now we have the building blocks. We understand the basics of machine learning, and we understand some of the basics of the data we're going to put in as vectors. So machine learning, it's all about finding patterns in data. So let's say we have a little training data set here. These are our labels. This is what we want to try to be able to predict, right? We want the algorithm to be able to tell us what this is, and we're training the algorithm on 2 inputs here, x1 and x2. Does anybody look at this and just see what they think? This is the equation we're trying to solve for. Y, yeah. What is the relationship here between those x and the y's? We want to turn x into y. Yeah, you read off the bottom of the slide here. Yeah, if we basically double x2 and add it to x1, we get y, right? And this is what machine learning is trying to do. It's easier to do it that way than you pull out a piece of paper. I don't know if I'd be able to solve for this. If you just gave me those 2 things, probably stare at it a while and then decide to go do something else. So one just quick thing. In this class, when we're going to be talking about stuff that's multiplied, I'm not going to put a multiplication sign in it because it gets confusing because we often talk about x's. So if you see 2 things together, it means we're multiplying. And this shouldn't be, we do this already in algebra, right? So we can have, instead of 3 times a, we just have 3a. Instead of 5 times x1, we just 5x1. That's comfortable for people? All right. So the whole idea is that machine learning finds those weights. And let's go back to this slide. It's almost like if we had a weight term w here that was 2, if w equals double what this is, then we would have solved for the algorithm. Does that make sense? So in real life, we might not have like 5 instances of x1 and x2. We might have 10,000. And instead of x1 to x2, we might have x1 to x10,000, right? And so a way that we represent this is that we're trying to solve for y as our labeled data, and it's going to be a combination of the weight multiplied by the feature, W times X, and that the number of times that we do this is the number of instances or features in our data set. Does that make sense? That's what this really fancy math just means. It means basically this. So for this one, we have x1, x2, x3 times basically x to the nth power, maybe it's 10,000, 1,500. And at each instance, we're going to multiply a weight term that the machine learning is going to find by the feature. And then hopefully, if our weights are correct, we can predict y. Does that make sense? Questions, comments?
So is it like the weight for every column?
Every feature that's important is going to have some kind of weight term, and then you're adjusting those dials, right? You're learning, your algorithm is using gradient descent to figure out what that weight term should be. That's why we covered gradient descent in the bottom of the bowl. So yeah, let's try to figure out on this example we just covered, the weight for our x1 is 1. We don't do anything to it. It's really not important. I put the 1 there so that you know it's there. But the real important weight for this very simple machine learning problem is 2. Once you figure out that W2 equals 2, you could solve it, right? Make sense? Yeah, pretty cool. So in real world, we might do this with the classic case that you will cover if you took just a machine learning class. The first example they'd use is calculating the price of a house, and you know the number of bedrooms and you know the square footage, and you're trying to figure out what weights do you put here in order to be accurately predicting the housing price. And again, it's this equation, which looks scary, but it isn't really all that scary once we understand what these terms mean. A lot of times growing up, I thought I was really bad at math because I would look at stuff like this, I'd be like, there's no way I'll ever be able to do it, right? And then as you start breaking it down and thinking about it theoretically, it makes a lot of sense. This is called linear regression. Yeah.
So I guess we call that a sigma and 2 and the I equals 1. That just means sum. Is that what you said?
Yeah, that's sum. We're summing up all the values of multiplying our weight by each feature. And in this case, on this data set, we have a 2 here because there are really only 2 inputs into our model.
Right. But if there were more than 2 inputs, you would just
It'd be 3 or 4 or 5, or a lot of times we just say n. Yeah, because the n number of features that you have is how long that equation is going to be, right? And we could solve for this very simple one, figure out the weights, a classic linear regression. It's going to learn that the weight 1 is 50,000, weight 2 is 100, and then we could give it new data, and if you knew the number of bedrooms and the square footage, it could tell you what it thinks the house should cost as. Pretty cool. Wait, isn't what we just did, multiplying weights by the inputs, isn't that a dot product? I think it is. I think that's exactly what we're doing. We're taking a dot product of our weights, a dot product of the feature and the weight. Which is why we cover dot products. And what are dot products telling us geometrically? How far away those things are. And so if we're really far away, well, we might need to use some gradient descent to get to a point in which we have less distance.
When you say far away, do you mean far away from,
how far away 2 vectors are basically from each other. That was that GIF that was going around. We knew that if they're orthogonal, it's 0. If they're in the same line, it's 1. And then we'll get a kind of this nice circular arc in terms of distance as we go around. Well, that's cool. So our dot product, if this is what the dot product is, that looks a lot like what we're doing right there. Cool. So the perceptron that's what it's doing. I like to think of it as analogy is I wish I had a real light switch, but it's we're summing the inputs, our x's with our weights, plus a bias term, which we'll cover in a little bit. And if we reach the activation, if those are the right combination of things, it's like we flip on the light switch. So we hit the activation function, and then we make a prediction. Cool, yeah. So we have our weights in a perceptron. We have our bias term, which I know I've been saying we'll talk about it. And then we have our activation function. And we get to decide what the value for the activation function is. It could be 1, 0, it could be 3, 4. That's arbitrary, but it's just we get to kind of decide when we flick the light on and off. And in a neural network, you get to pick the mathematical function you want for activation, but that's about the control you have over it. So here, our inputs are maybe these columns. Our weights are being learned by the model, and then we have this bias term. So the perceptron starts by computing the dot product of all the weights in our inputs. It sums those, and then it adds that bias term onto it, and then in this case, our activation function was if it's more than 0, apply the activation, and it met that, so it went forward. Neural networks, deeper structures often have a back propagation, where it's sending that information back to retrain. Cool. Questions? Okay, you're starting to get into theory land. So let's go back and think about this, not in algebra, but in terms of geometry again. This is what the perceptron is doing. It's bringing a weight term, and it's getting our decision boundary by taking the bias term and the weight term and making sure that they're orthogonal, where they come to 90 degrees. So we have two different parts of data, class 1 and class 2. The decision boundary is where the dot product of our weights and our features plus our bias term equals 0. Well, how do we know it equals 0? I told you already that things that are orthogonal or 90 degrees are going to enter 0. And this is literally how the perceptron makes that distinction between different parts of our data set. I think that's cool, but then a lot of things I think are cool, other people don't think are cool. Hopefully you think this is cool. I won't judge you if you're like, this is not cool. So again, the weight vector is perpendicular to the boundary, right? That's why the dot product sums to 0. Pretty cool. And we talked about that in machine learning, the perceptron has to try to find those weights itself. So it makes a couple different tries, and in this one, it's just really lucky. It comes to the right decision right away. But in real life, that's almost never going to be the case. It's going to try a bunch of different tries. At every point, it's doing that kind of math that we talked about until it arrives at a decision boundary between our two data sets. Maybe they're cats and dogs, right? One of the first instances of this was number classification. Woo, all correct. Cool. That's how it works. Well, how do you do this for an image, right? Well, we already know that an image is just a grid of pixel values, right? I'm not using the 0 to 255 here. I'm using the 0 to 1 normalized just because it's easier. But we could read. We know that this is what the computer sees, and we've talked about filters already, so you guys are just completely up to speed. We're going to go through. We're going to get all those values. Hey, this is like last week. That's not very hard. Well, then we might read all of those values into one big array. This would be a 63-dimensional array in this case, because you have 63 different pixels. Okay, we feeling that? Not too hard. It's a big array. That n equals 63 here instead of 2 or 3. Yeah, and that's cool. Yeah, oh, I'm sorry, 64. Oh, I'm just so bad. And a lot of times you'll see this. X is within the set of real numbers that is 64. It's just telling you the depth of the length of that array. Okay, cool. So we have see these as like our arrays. It's just a bunch of numbers kind of in brackets. And then we're trying to figure out what our weights are. Take the dot product of those two, the pixel and the weight, and then a bias term, and we're trying to sum and see if it meets that decision boundary to fire. So the weight is like, how important is this pixel in terms of being a 6 or a 7 or a dog or a cat? That's cool. And again, just looks like that. So that's your mathematical equation for the perceptron along with some other things. Some problems with the perceptron and why we don't just stop with the perceptron is one, it finds one decision boundary, but you can't really say that the decision boundary it finds is the best decision boundary because it basically stops when it has a decision boundary where we have a dot product of 0 and we can fire, right? And it took a while for people to figure out ways to like actually be able to say this is the best fit decision between our two things. And this has a real world consequence. If the decision boundary is there or here, what if I have data right here, right? Is it going to be able to classify it correctly? So support vector machines, which we'll learn next week, can actually tell you this is the best fit line. So that's a pretty big one. What would be maybe another thing that would be a problem for the Perceptron? Could there be types of data that aren't separable by making a line through them? Right? Yes, there could. Not everything is going to be what you learned in grade school, getting a linear function. And if the data is not linear separable, the Perceptron, you see, is trying, it could try any one of these. It could draw lines anywhere. It's not going to be able to separate these two types. This is called the XOR problem. This was, yeah, I mean, it can't be solved with the Perceptron. There's no straight line you can draw that separates these two labels, or these two labeled data sets from each other, right? So this is cats, and this is dogs. The Perceptron just can't do it. Does that make sense? Kinda? Well, the Perceptron works by dividing data with a linear, that's linear separable. Linear separable means you can draw a line through it to separate it. You can't draw a line that separates these two data sets.
So what would a data set like that be? Like if it's cats and dogs, would it be a different classification?
It's nonlinear data. And this is where k-nearest neighbors can solve for it. Yeah. So let's talk about nearest neighbors. These are all ways of classifying that are not linearly separable. You can't draw a line through this data and say, hey, I can do it. But that doesn't mean that the data is useless. I like to think of this example, 1854. John Snow, he's both an anesthesiologist but also an epidemiologist. He's living at this time in which you kind of do everything if you're smart. And there's this really big cholera outbreak in London in the Soho district. And so he starts mapping out all these black dots are wells. And he starts to think through, can I map out, maybe there's a cluster here of one bad well where everybody is getting sick. And he figures out by mapping it out in this way that the Broad Street well seems to be where people are getting sick everywhere, but they're really getting sick here. If you live within this kind of area, your chance of getting cholera and dying is much higher than if you're over here, right? He starts to basically cluster these wells together, and they figure out that the Broad Street well is basically contaminated with sewage. The brickwork around the well is failing, and sewage, back in the day, you dumped your sewage out on the streets. It's getting into the well. I know, it's gross, right? But it's also, what he's getting at is this concept of Voronoi cells. That basically a nonlinear separated data, where you can't draw lines through it. One thing you could do is basically, if you know these are all wells, you could decide, draw cells around them, and then anything that is closer to this cell than this cell belongs in this group. And that's literally what these lines are doing. Anything within this space is closer to this cell than it is to that cell, or that cell. Does that make sense? So there's a way of categorizing data now in a machine learning technique that isn't about linearly separated data. We're not calculating dot products, things like that. We're still going to calculate distance, but we're going to do it in a more geometric sense with Euclidean and Manhattan distance. Does this make sense? Okay, cool. So this is a cool visualization of what's going on here. Is each one of these cells is kind of being projected out into space, and they have different sizes because their cell location is in different areas. So if you're right down here, if you're right here, you're still in the green cell, but as soon as you go over there, you're in the orange cell, and you can be classified as an orange cell or a green cell. And obviously, we could put other semantic labels on these. These could be cats, they could be dogs, they could be, locations for the post office, right? So I guess the question is, how do you measure distance? If this whole series of machine learning algorithms of nearest neighbors is based on calculating the distance between cells and then classifying these big region groups, well, how are you calculating the distance? And here we see that there are different ways to calculate distance, right? On the left, we have Euclidean, and on the right, we have Manhattan. which are two of our classic ways of doing it. It sounds complicated, it's not though. Euclidean distance, we're trying to figure out, we're Jon Snow, we're trying to figure out, here's a house, which pump are they probably getting their water from, or what cell do they belong in? With Euclidean distance, we're just go ahead and taking literally the distance between those two things. Not very hard, not hard at all. Does that make sense? Manhattan distance, a little different, because Manhattan distance is going to basically, instead of having the hypotenuse, it's going to solve for the other portions of it. Manhattan distance comes from the idea that Manhattan itself in New York is a series of streets, so you can't like cut through buildings the way the crow flies. Sometimes you literally have to navigate the space in a different way. So I think that this is like how birds fly, and this is how people maybe move through a space. So just two different distance calculations you can do. So how do we do this? How might we classify something like numbers as images using nearest neighbors? Well, each one of these, we talked about them having 64, they're a 64-bit number, and we're just going to chart them out on space, see where the vectors land, and then we're going to do some distance calculations. So we have 3, 8, 2. Nice. And then we'll just compare the distance between these different vectors. And we'll say the new image coming in, this unknown image, well, it looks closest, it belongs in the 8 cell. Pretty simple. That's like a weird 8, but maybe somebody drew it in a weird way. Maybe I have like a screen and you draw things with your finger, and then we take those pixel values and put them in. You can see how somebody could make an 8 that looks like that, but we still need to classify it as an 8. Do this, sometimes you can do like optical character recognition this way, the way that like the post office can, you write it down and then the computer can read it and tell that you live on 123, I don't know, Rose Lane or whatever. Sometimes nearest neighbors help with that. It's called optical character recognition, OCR. Make sense? All right, so the full pipeline, we take that 7x9 image, we turn it into vectors, then we just compare, that's moving too fast. We compare it to the vector space that it's in, we apply a nearest neighbors algorithm, and then as long as we've labeled some data before, we can interpolate what that number is from the label. Sound good? Now, there are, again, we have linear boundaries, and then we have nonlinear algorithms. Ransack, which we covered last week, is a form of linear modeling, but not everything can be modeled linearly. So yeah, this is an example of what that might look like, not with sewers, but like this is the new data point, and we have these classified through nearest neighbors. You can't see the Verneuil cell, but then it's just saying, hey, it's nearest to class B, so yeah, let's do it. That's a B, not an A. What could be a problem with this? Where it's close? The fact that it's only comparing it to one neighbor. Wouldn't it make sense to compare it to k number of neighbors? Just like we did a k-fold algorithm. How many cuts do you make when you mix a data set? Maybe we want a k nearest neighbor, where k stands in for the number of other points we consider it to. Generally, k nearest neighbor algorithms work best when it's odd. That way you never have a situation where you're dividing by like equal numbers. So yeah, one nearest neighbor, we can do that. That's what we've already learned. But what if the point is, yeah, as we expand out, we see that it hits a bunch of different things. It's kind of hard to see where it is. Maybe it's located equidistantly in space. So with one nearest neighbor, we can predict that. But what if we did more than one? What if we went out and we calculated 2, 3, 4, 5, right? And then we looked at the distances there. It could actually change. Now it's saying, well, this is a class A. Before it was saying this is a class B. So nearest neighbors might be a way to get a little more refinement in a confusing space. So let's just look at how the number of k changes the prediction. So we add more k's, we're comparing to different points. So if k equals 3, it's class B. K equals 4, it's class A. Now, I'm picking a very confusing one, right? A lot of data points aren't going to be like this. They'll be located firmly, and it doesn't matter how number of k you have. But we can see that k might be one of these parameters that we can tweak, just like a learning rate, to try to see what the best approximation is.
How do you know what the best K is?
Well, we'll talk about it. Yeah. And this is where there's like an art and a science. So we can even see that the decision boundaries, those cells change depending on the number of nearest neighbors you have. So 1, just looking at 1, k, we get to define the k. And a rule of thumb, start with k equals the square root of the number of neighbors you have. Just start there. And then you can move around and see if it's good or bad. So let's look at some applications of this with the 7 minutes we have left in class. Ranking systems like Netflix and Spotify often work. Underlying it is a nearest neighbor algorithm. It's saying that I can take your preferences in terms of songs, in terms of movies, I can plot them in a vector space, and you are not all that unique. If you listen to this artist in that space, and your buddy listens to that artist as well, but he also listens to another artist, you might like that artist that your buddy listens to because you listen to the same music. This is like, a lot of recommender systems use nearest neighbors. In economics, we can try to, just like we calculate distance, we can try to make predictions on stock and housing prices also using nearest neighbors, especially if the data doesn't seem to have a good concept of linearity. This is a good example of this. It's like, where should the line go? It probably should start up here, but if we project out, well, we're missing a lot of data here. Maybe it actually should be a little more like that. Image classification. We talked about reading in an image as this big, long array of numbers where every instance in that array is a pixel value. So we could just do that, and we got some pandas over here, we got some cats over here, we have some dogs over here. We're able to group them using, Euclidean or Manhattan distance or another distance metric. We bring in that new array, which in this case is a dog. Its distance is going to be hopefully closer than it is here. As long as those concepts, the semantic categories that we refer to it, dog, cat, are actually meaningly distinct. I think the dog versus bagel is one that doesn't do really well because dachshunds sometimes look like bagels when they're curled up. Does that make sense? One problem with k-nearest neighbors, and this is a little hard to wrap your head around, I think. But basically, if it's a dimension, we talk about 1-dimensional, 2-dimensional, 3-dimensional data, right? In this class, we've been projecting back and forth oftentimes between different dimensions. And one thing we have to be aware of is that if nearest neighbors is calculating the distance in a certain dimension, that as we add more dimensions, the things actually get further away from each other, okay? And this might be hard to understand why, but at this point, just accept that as a rule, right? As we add more dimensions, things get further away from each other. So we have this 1-dimensional space. Things are really closely grouped together here, and then they start to get a little further. Like there's a lot more distance in this dimension in terms of white space than there is here, and then it just gets worse and worse. So a little kind of graphic that shows you that. It's literally calculating the distance between on a 1D plane and then the distance in a 2D plane. Now we're getting 1.12, distance in the 3D plane, 0.225. We can see that distance is increasing. What does that mean for when k-nearest neighbors might be a bad fit? Huh?
You can group things anymore if the distance.
Yeah, if we're working in high-dimensional spaces. So let's think about this as an Excel spreadsheet. The more columns we add, that's more dimensions. If we approach really high-dimensional space, nearest neighbors gets impossible to compute. It's computationally expensive because it's a non-parametric model, so it has to look at all the instances to make the inference. And then it also, the distances it's calculating start to get so big that you can't make any meaningful distinctions. It's like people often say that no one can hear you scream in space. like if you're actually literally in space and you screamed, because you're so far away from everything, it's also vacuum. They say that about K nearest neighbors, that like as you go up into high dimensional, the distances are so long, so far away that they're really meaningless. It's like saying I'm 900 light years away from something versus 898. Well, shit, that distance is so big, right? It's not a good way to classify things.
Is it just K nearest neighbors that
Has this problem? In terms of what we learned so far, yes, without a doubt. Because this is a property of calculating distance through something like Euclidean space. So if the distance in different dimensions increases relative to the number of dimensions, then your Euclidean distance is going to be a problem. Now, if we are calculating distance in other ways, maybe not so much. And a lot of the really far out stuff that you do in machine learning is you sometimes reduce dimensionality to basically get to the features that really only matter. I give you that housing data set, I give you 1,000 different columns, including the number of coffee makers, whether the person on the tile is male or female, distance from downtown, crime rate, bedrooms, how many electric lawnmowers the person owns, whether they enjoy watching Love is Blind on Netflix. I just give you everything. I give you all the data. We live in a big data era. Probably a lot of those columns have very little to do with housing price, right? And if we had an algorithm that could go through and just basically tell you, these are the ones that you need to pay attention to, we might find the principal components of the problem that actually make sense, which is exactly what we're going to do next class. We're going to look at ways that we can compress dimensionality when we're given a lot of data and just figure out the things that actually seem to be important to make the prediction. That is what PCA does. That's what you're going to do your reading on in preparation for Thursday. It's going to take things and look for and try to compress them down. And then we'll also learn about support vector machines that day, which work in the other way. They say if I can't find the problem in this dimensions, maybe I'll go up to a bunch of different dimensions, maybe even infinity number of dimensions. And maybe in that space, now all of a sudden, the vectors are in such a way that I can make a meaningful relationship between them. Right? Like, can I project into different spaces and then get associations that I couldn't? Just like for the 2D space with the pixels, we saw that it was a lot easier to calculate an edge when we were in 3D space because we could just take a slope. Yeah, so we're going to play with dimensionality a lot tomorrow or on Thursday, which is far out, but I think really cool. So yeah, this is like in high dimensional space, like how can you really say that there is any distance at all? Which I think it's interesting. Low dimensions, small neighborhood. We can calculate that. High dimensions, a little harder to do. So what can we do because of the curse of dimensionality? Well, we could use like something like PCA to reduce the number of dimensions and then apply nearest neighbor to it. Does that make sense? Fist 5, how are we feeling? I know I'm 1 minute over. Good, okay, cool. I think that one thing I will think a lot about for class this week is giving you some cool